Hello, my name is Carter Strickland and welcome to Lab 5 of Physics 2211 Curveballs. In this lab, we'll analyze two balls that are thrown and discuss why their movements differ. Some principles to keep in mind for this lab are the kinematic motion principle and Bernoulli's principle. The two equations we'll be using to model our experiment today are the kinematic equation, specifically the equation relating to the y component of an object, as well as Bernoulli's principle. Since this is something we haven't discussed in this class though, we won't be going into great detail on it, but an important note is that it claims that pressure is inversely proportional to velocity in a fluid. In this video, I threw two balls, a knuckleball and a curveball. The knuckleball has no spin and the curveball has been given backspin. They are thrown with the same angle, strength, and go roughly the same distance. However, you'll notice a key difference in the trials which disagrees with the fundamental principle we have talked about in this class. So starting from the basic height kinematic equation, we're able to quickly see that mass has no effect on the time a ball spins in the air. The only determining factors are how high the ball started and how hard the ball was initially thrown. This means that as long as these conditions are kept consistent across all experiments, that the time the ball spins in the air will be the same for all tests. This begs the question, why didn't our test examples earlier follow this rule? Did I throw one of the balls too hard? Was I squatting down in one of the videos? And while, yes, the test conditions were not perfect, there is a stronger influence at play here that I would like to talk about. This is where the earlier mentioned Bernoulli's principle comes into play. Now, the exact Bernoulli principle are on the scope of this entire video, but one important detail that we need to note is that pressure is inversely proportional to velocity. Therefore, slower velocity equals greater pressures. What does this mean for our baseball? Well, when the baseball is thrown, the baseball can have spin. Well, in all our previous examples, we considered a ball that had zero spin and zero air resistance. In the real world, that's not actually what happens, and in fact, for baseballs, the exact opposite happens. As the baseball spins, it comes into contact with incoming air. Air that meets the top of the ball will go around the ball in the direction of motion, but air that meets the bottom of the ball will reach conflict and has to fight to go around. This causes the velocities of the air on the bottom of the ball to be slower than the velocity of the air at the top of the ball. As we just noted with Bernoulli's principle, this means that there is a higher difference in pressure at the bottom of the baseball than above the baseball. With a higher pressure below the ball and a lower pressure above the ball, we have a net pressure pushing up on the ball. We have to remember gravity, which is also working heavily against this positive pressure. However, this pressure does have enough of effect that it allows the ball to stay in the air longer than a ball which is thrown without spin, and therefore it does not incur any positive pushing pressure. This is why the video on the right, where a curveball is thrown, allows the ball to stay in the air longer than the ball on the left. Despite having the same initial velocity, you may have noticed that the curveball took longer to reach the ground. Now this disagrees with one of the fundamental principles we talked about, which is that mass has no impact on how long an object should take to reach the ground. In fact, any object thrown with the same velocity and from the same height should reach the ground in the same amount of time, disregarding air resistance. But as you can probably suspect, air has a big part to play in this, and I'll pass this over to edited Carter here later to go into further detail on this. All right, thanks, Fesman. That was really fun. This brings up two really big questions, though. In our experiment, the ball had backspin and rose up. What would happen if the ball had forward spin? Well, you can probably imagine the opposite. The ball would actually be forced down to the ground. This is actually what is more commonly accepted as a curveball in baseball, whereas what we threw earlier was still a curveball, but would more likely just be called a fastball, as those tend to curve up. We also can ask why the ball is so prone to influence from the air. Well, this is because of the imperfections on the surface of the ball. Now, given that the ball in the video was just a crumpled up piece of paper, as well as being light, it was going to be very prone to being influenced by the air. But in real life, baseballs have stitches, and it's those stitches as well as scuff marks from hitting the dirt and getting caught in gloves that allow the ball to really be influenced by the air as those imperfections abrase and cause disruptions as it tries to fly. To conclude and acknowledge a few possible sources of error, I'd like to say that I'm aware that I probably didn't throw the ball perfectly the same in both tests. I would also note that there may have been fluctuations in the air status of the room due to the air conditioning, and that I may have thrown the ball harder or softer with each test. But overall, this doesn't take away from the claims and ideas we've been able to discover in this lab, as the principles still hold true and had noticeable impact on the ball, regardless of the starting conditions. The largest concluding point I would like to make, though, is that fluids such as air make massive impacts on the movement of bodies, and it's important we understand them. It's this understanding of the influence of air on a baseball that also allows us to understand how air allows planes to fly and F1 cars to reach incredibly high speeds. Combining the simple nature of the laws of physics with the complex real world can prove challenging, but I believe that's what makes it all this a blast in the first place. Sometimes you'll have to walk away and come back later, but the rules won't change, so progress never has to stop. Overall, thank you so much for watching. I hope you have a great rest of your day.